Welcome back. Before we move on from chapter 5, we're going to discuss a little bit about the topic known as scientific notation. And then we're going to dive into chapter 6, specifically looking at section 6.1, and we'll discuss the topic of factoring, which we've already been introduced to previously in this class, but we're going to dive into it with a little bit more detail. All right, so scientific notation. What is it? When is it used? Why do we use it? Basically, guys, depending on the scale of different engineering and or construction calculations that you may have to perform in the industry, if you're a CNC machinist and you're working on machining out some sort of a precision part, like say a precision bearing for an oil industry application, or you're a welder who might be working on, at a different scale, okay, you might use one type of measurement to measure something that's super, super precise. And then we might use a different type of measurement if we're measuring something that might be the size of, say, a football field or bigger. And so how this works is that at the scale of precision devices, so this would be at the scale of, say, the electronics in your computer, you have things that are designed at 1,000th of an inch. So 1,000th of an inch, what is that? Here's 1,000th of an inch. Note that we use two of these little, they look like quotation marks, but it's just one set of quotation marks, and this means inches for the American system. And the scale of 1,000th of an inch is for things like electronics. Microprocessors might be a little bit smaller than 1,000th of an inch. In fact, they're usually going to be smaller than 1,000th of an inch. But precision electronics, microprocessors, precision equipment. These are all going to be at the scale of 1,000th of an inch, which is roughly the thickness of a sheet of paper. If you want some sort of a technical measurement, like just pick up a piece of paper and notice how thin the piece of paper is, that's going to be roughly 1,000th of an inch. All right. So at 1,000th of an inch, you're dealing with things that are the size of electronics, microprocessors, precision testing devices, so on and so forth. And then once we get to, say, the size of, kids' toys, right? We're no longer necessarily measuring in thousandths of an inch, but rather you just measure in inches. So we use the measurement inches for things that are the size of children's toys, handheld tools, car wheels, etc. So at the scale of a car wheel, you're using a measurement called an inch. And then once you get beyond that, if you're talking about large carpentry applications like building a cabinet, say, in somebody's downstairs basement, then you usually pick a new size measurement device. We call it the foot. So the foot is one level up from the inches. We say that 12 inches go into a foot. And the reason we pick 12 inches, as we discussed previously in this class, is that basically 12 is what is known as a hypercomposite number. And what hypercomposite means is it just means you can divide it into a number of different smaller increments evenly. So I can take 12 of something and divide it by 3. I can take 12 of something divided by 6. I can take 12 of something and divide it by 4, so on and so forth. Whereas if you took the number 10, you can only divide 10 by 2 and 5. Okay, so 10, even though it's convenient for us in terms of counting purposes, like we have 10 fingers, for example, 12 is actually really, really nice because you can divide it by a whole bunch of quantities and thereby essentially avoid the use or needing to use a bunch of fractions for all of your calculations. You can just switch anytime you would have to have a fraction of a foot to the comparable amount of inches that one would need. Okay, so that's the reason why 12 inches goes into 1 foot. It's actually very clever Unlike some of the Europeans would have you believe, the European system's actually less convenient from a practical I need to build something perspective, because then you have to, have calculation devices usually at your disposal, because dealing with decimals is very inconvenient from a calculation perspective. In fact, dealing with fractions in many instances is going to be the way to go whenever you're trying to do something that is useful in the real world. If you were doing it by hand, you probably want to use fractions instead of, say, the decimal system. But that's neither here nor there. So a level up from inches is what we call a foot, and this would be measuring things that are the size of cars, cabinetry, cabinet cabinet tree. Things that are the size of, say, houses, etc. So on that scale. And then up from the foot, we say that 3 feet goes into a unit called a yard. Now, a yard is a little bit of a perplexing unit of measurement. I believe it's essentially the Western world's version of a cubit. I could be wrong about that, but basically a yard is almost the size of what is known as a cubit, which would be a unit that was known to, say, the Egyptians, and was used a lot by the Semitic peoples of Mesopotamia. So the yard is basically the American version of a cubit. I should say the United Kingdom's version of a cubit as well, because the UK also has a unit called the yard as well. So for the Americans and the United Kingdom, this is our version of the cubit. And what we use yards to measure is, we're going to use a yard to measure things that are a little bit less convenient to use feet. So for example, if you've got something that on the scale of, say, a silo, a grain silo, okay, these big, massive industrial grain silos, or something that's on the scale of, say, a number of football fields. It's easier for me to measure the range of something if, instead of saying a football field, I say, okay, that's 100 yards. Right? A football field's exactly 100 yards wide, and there's a reason for that. Like 100 yards is just the right amount of distance for many different applications. Whether you're talking about sizing in, say, your shooting, if you people who are hunters or people who are sportsmen shooters will know that you usually measure out the precision of your gun to 100 yards before attempting to, say, shoot out to twice or three times that distance. um so yeah, we use yards for these measurements that are, football fields long. You'll use yards if if you're talking about like an artillery bombardment. You're like, oh, aim our artillery out to 2,000, 3,000 yards, or at the scale of 3,000 yards, you would probably switch over to discussing units like a mile instead of yards. Okay. So once you get up to a sufficiently large size, we switch up to the next unit of measurement. So up from yard, we talk about things in terms of miles, and that's going to be as good as it gets for the American system of measurement. So a mile, you should know that there are actually two different forms of a mile. There's the land mile, and then there's also a nautical mile. The nautical mile is an interesting unit of measure because it's based on the angle of the Earth. So as a ship moves around the globe, because the globe is a sphere, then you can actually accurately place the distance of a vessel from point to point using a unit called a nautical mile, because a nautical mile, as I understand it, I believe it's 1/60th the degree of the Earth. So if you were to if you were to partition the Earth into 360 degrees around its longitude, at longitudinal axis, around its axis, said another way, then you took 1/60th of one of those degrees. That is exactly a nautical mile. Okay, that's my understanding of where the nautical mile comes from. And I could be mistaken on that, but that's my understanding. So there are two different types of nautical miles. I'm sorry, there are two different types of miles. There's the land mile and there is the nautical mile. These are both for measuring distances that are greater than 1,000 yards. All right. So as we go up in our in the size or in the scale of some phenomena that we might be trying to measure, we're going to need to move up in terms of the ability to actually measure that something. Now, what's interesting is that in mathematics, when we go up in scale, we usually go up in scale at a very precise increment. So even though, say, the inches to a foot, we say that we have, 12 inches to a foot. The scale at which the inch starts to become a little bit cumbersome is going to be when you're dealing with, say, 100 inches. That's when probably measuring in feet would be better than measuring in the inch. Is like when you get to 100 inches, that's probably a good time to switch over to measuring in feet instead. So, um, basically, we say that you can only measure something accurately within an order of magnitude of 10 raised to the 3. So 1,000 units. Once you start getting beyond 1,000 units, you really can't measure anything beyond that very accurately. Um, and we also say that you can measure something accurately to 10 raised to the negative 3 units. So 1/1000th of a unit of whatever you're measuring. So we measure, say, precision tooling using 1,000th of an inch or 0.001 because that is the threshold by which the inch as a unit becomes meaningless. Like anything smaller than 1,000th of an inch, well, it's certainly possible for you to actually measuring it. It would probably be best to simply move to a new unit of measurement to begin with and start over in terms of your measurement. Okay. So you say it for any given system of measurement, you can measure up to 1,000 units of that system, and as small as less than 1/1000th of that unit of measure. Now, you'll note I used 10 raised to the third, and I was able to precisely know that 10 raised to the third was 1,000, and I was able to know that 10 raised to the negative 3 was exactly 1 over 1,000. How I knew that was because of what is known as the scientific notation. And so here's an interesting fact about the number 10. If you take a number, say we have the number 3, and we multiply by 10. What's going to happen to the number 3 is that, well, 3 times 10 gives you 30. So it's almost like the number 3 was moved over exactly one space and you slapped a 0 behind it. Now check it out. If you have 3 times, excuse me, if you have 3 times 100, you're going to slap a 3 down. But we know that 3 times 100 is exactly 300. So at this point in time, it's almost like the difference between 3 times 10 giving us 30 and 3 times 100 was just that we added an extra 0 to the back end. And of course, 3 times 1,000 gives us 3,000. And 3 times 10,000 gives us 30,000. 3 times 100,000 gives us 300,000. Okay, interesting. Interesting. If we multiply by what is known as a factor of 10, it's almost like my unit, whatever the unit happens to be, is shifted over by the specific number of places, the specific number of zeros that I might have. If you have 1 0 here, you put your 3 and you slap 1 0 down. If you have 2 zeros, you put your 3 and you slap 2 zeros down. If you have 3 zeros, or multiplying by a unit of 1,000, you slap your 3, you put 3 zeros down. If you have 4 zeros, so on and so forth. All right. Another interesting fact is simply that I hope everybody will remember from our previous chapter that 10 raised to the 1 should give me 10. Okay, just by definition of exponents. Okay, cool. But if we do 10 to the second power, that's going to give me 10 times 10, which is interestingly going to be 100. And if I have 10 to the third power, I've got 10 times 10 times 10, or 10 to 10 times 100. So I can slap my 10 down, and then what do? I'm going to add two zeros because I'm multiplying by 100. So 100 has two zeros. So I will write 1 followed by three zeros. I have 10 to the fourth power. I have 10 times 10 times 10 times 10. 10 times 10 is 100. 10 times 10 is 100. So now we've got 100 times 100. And look at this. We have 100, which is our initial unit, and we multiplied it by 100. So that has two zeros. Here are my two zeros. So I should get 10,000. So every time you raise 10 to the power of something, you're going to produce a number which has exactly 1 as a digit that's out in front, followed by a specific number of zeros. And it happens that the number of zeros that come after the number 1 or the digit 1 in your number are going to be predictable based on the exponent itself. So 10 raised to the 5, all I have to do to be able to calculate this is put a 1 down, and then I need to add 5 zeros behind it. That is going to be exactly 10 to the 5. And it just is a feature of what's happening whenever you multiply by sets of 10. Okay, so if I have 10 to the fifth, it's 10 times 10 times 10 times 10. 10 times 10 is 100. Times 10 gives you 1,000. So this is 100 times 1,000. So you write your 100 down, and then you're going to slap three zeros after it. Okay, and you get, what is that? 100,000? It's not exactly 100,000. It's going to be, yeah, it is 100,000. Okay, I get 100,000. 10 to the sixth, 10 times 10 times 10 times 10 times 10. And that's going to give me 1 million. Excellent. Because it'll be 1,000 1,000s. So I'll get 1 million. All right, excellent. So basically, the idea with what is known as the scientific notation is that it allows us to perform really, 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 really ridiculously big calculations and exploit this fact that you can't measure something that's super, super small or super, super big anyways. So there's no point in pretending that you don't have a bunch of error. There's no point in pretending that you can get a precise answer at the end of the day. And what do I mean? I mean, even for a formula like the force is equal to mass times acceleration, and this is a very basic formula that's going to come up in your physics class if you do take physics 1, this can quickly get out of hand depending on the mass of an object and depending on what the acceleration of that object happens to be. Okay. And so, if we try to pretend that when we multiply these numbers, we're going to get an exact physical phenomena. Yes, when we multiply the two numbers, you can perform that calculation and you will get a precise answer. But in physics, what we know is that the physical world isn't going to be as precise as the math makes it out to be. So even though we have this nice little equation, force is equal to mass times acceleration, what's actually happening in the physical world is that there are all of these things, all of these factors that we can't take into account. For example, say you're shooting a bullet. The movies, Hollywood makes it out like a bullet is just going to fly perfectly straight at a specific target. And therefore, Hollywood makes it out like a police officer could theoretically just, shoot a bandit in the leg or in the foot and just, mortally wound the bandit, but not kill the bandit. And of course, the public then gets outraged because they say, well, I saw this in the movies. Why can't the police officers actually do this? But anyone who's enrolled in the police academy or anyone who's enrolled in the police program here at SCC and has, maybe practiced with firearms will tell you that when you shoot a bullet, what actually happens is the same thing as shooting a cannon. So when you shoot a cannonball, the cannonball itself actually has an arc associated with it. And so when you have a handgun, and here's my very crudely drawn handgun, there's also a very, albeit small, amount of distance that the bullet will fly in an upwards direction as it soars in an arch towards the target. So it doesn't fly straight, it actually arches up by a small amount as it's flying through the air. And this arching is due to a number of phenomena. On the one hand, it's due to the lift of the bullet. So the bullet is flying through the air. It has some lift associated with it, and it will lift up. And then it also has to do with the fact that air is a compressible fluid. So it's compressible. Air is compressible. You can get compressed air tanks, right? And what that means is that because the bullet is flying so fast, it'll encounter different pockets of air, and depending on where you're at, your altitude, et cetera, the wind, the speed of the wind on a given day, the amount of arcing is going to change in one direction or another. And so the bullet is going to hit a target. As it turns out, it hits a target in like this kind of arc circular shape. So if you keep shooting like 100 bullets at a target that's 100 yards away, what you'll see is that even if you've lined up your gun perfectly with the target, your bullet is going to hit in this circular pattern, depending on how accurate your gun happens to be. They'll sell guns based on the spread of the bullet, and they'll try to, market this gun is super accurate out to 1,000 yards or whatever. So at any rate, that's a little bit of a digression, but it does set the table for now. While at 100 yards, we may be making this calculation: force is equal to mass times acceleration, and we know that we're going to get the spread of a bullet. At 1,000 yards, the spread of a bullet is even going to be wilder, much wilder. If you have an artillery and you're bombing an enemy encampment, and a modern artillery can bomb an encampment that's like 20 miles away, 30 miles away, 40 miles away, and people are like, why didn't my artillery shell hit the target? Why is it like a mile downrange? Okay, this is the reason, because even though we have all of these equations that might try to model these physical systems, it's just a model. When you actually run the numbers, there's error in that calculation. It's just that the error doesn't show itself in the numbers. It's an inherent part of the physical universe that you live in, okay? So math is a bit deceptive. Math makes things out to be that you can perform this sequence of calculations. If you only had a more precise formula for performing the calculations, you'll be able to get a much more accurate answer. And while that's true to some degree, as our technology improves, as our understanding of reality improves, we can start to take into account a lot of these physical forces that act on us that may be more mysterious at a basic level. There's still some unknowns that are thrown into play. There's still a lot of things that we can't take into account. And so at scale, we shouldn't pretend that our answer is accurate anyways. Okay, this is all to say, when we've got a massive number, like let's say we're doing a calculation and we've got this number 38,547,249,342, and we're multiplying it by 43591278425. Okay, these are just massive numbers, guys. Like this is 43 billion, this is 38 billion. At the scale of a billion, think about it, guys. Think about it. When a politician says $30 billion was spent on this project, $35 billion was spent on this project. Does it really matter to you psychologically if 30 billion or 35 billion was spent on a specific project? Most people would say at the scale of a billion, it's just a lot of freaking cash. Okay. So 30 billion, 35 billion, it's so big, it's so much, it's a ridiculous amount of money that it's at such a scale that is very difficult for us to even, for us as mere people to even get a grasp of. If you haven't been to, say, one of the central banks, if you haven't taken, say, a tour of the central bank in Kansas City, it's very hard for you to get a grasp of what $1 billion looks like if it's put all in one place. So this is a perfect example of where multiplying two numbers together is going to introduce a lot of extra work on our part. And so what I'm trying to say is, yes, we could go about trying to line up our numbers. 38, 547, 249, 342. And I can multiply this by 43, 591, 278, 425. I could do that. You could say 5 times 2 is 10. Carrier 1. 5 times 4 is 20. Plus 1 is 21. Carrier 2. 5 and 3 is 15. Plus 2 gives you 17. So on and so forth. We could do this and spend all afternoon trying to perform this calculation. But what if I told you that there's actually a better way? That even though we could do this and even though we could spend all afternoon trying to perform one calculation, there is in fact an easier way for us to perform this calculation that isn't going to give us a deceptive answer. Because yes, we can perform this calculation, but what we need to remember is that at this scale, it's going to be hard for us to even measure this quantity to begin with. This is one of the reasons why it's very difficult for America to reform its financial policies because what you'll see from various politicians is they'll say things like we need to rein in the debt. We need to rein in the debt. The problem is if the debts for the United States and the debts for the United Kingdom and the debts for France and the debts for Germany and the debts for Russia and the debts for China are at such ridiculous levels that by the time you were to account for the debt, you'd have to account for the debt again because you just spent all of your money. Like you couldn't account for the debt fast enough to be able to say, okay, this is what we have on hand and this is what we need to reform because it's at such a ridiculous scale. So when you're at that ridiculous scale, even being able to balance a basic budget becomes a matter where you need very, very sophisticated softwares to do it. And even then, it's a difficult task, okay? So the reality, I'm sorry to say, the reality is that when it comes to America's budget, that is a problem that is going to take a lot of thought to actually be able to reform, okay? Because it's probably going to take us, to a total shutdown of the government, a total reformation of the different, powers that be in Washington, D.C. to actually get control of that budget because it's at such a scale that short of doing that, short of having a new method of accounting for dollars other than the dollar itself, short of, say, what's called revaluing the dollar to a different unit of measure, it would be very, very difficult to actually perform these calculations. And it's dishonest to say otherwise. So it's dishonest for politicians to even pretend that they could do it without some very severe reforms. And it's just ignorance on their part, really. So, okay, so back from politics, we've got this massive number. What can we do? Well, if instead of writing a number like 300,000 or 30,000, so we have this 300,000, and we said that 300,000 is the same thing as 3 times 100,000. But we said that 3 times 100,000, here's my 100,000, is the same as 10 to the fifth. So now instead of 3 times 100,000, I could just write 3 times 10 to the fifth. And now I hope you can see that say I wanted to do a calculation with this number 300,000. Say I wanted to, I don't know, multiply 20,000 by 300,000. Okay. If I write 300,000 as 3 times 10 to the fifth, and I write 20,000 as, let's go over here to 20,000 should be the same thing as 2 times 10 to the fourth, according to our little chart, because 10 to the fourth is 100, I'm sorry, is 10,000. So 20,000 is just 2 times 10,000. So I could write 20,000 as 2 times 10 to the fourth. Then when we multiply these numbers together, by the associative law, we'll be multiplying 2 times 10 to the fourth times 3 times 10 to the fifth. And initially, it doesn't look like our life necessarily gets easier because now we have a bunch of exponents. So a lot of students are going to say, I don't understand why we're using a bunch of exponents. But if you, at this point in time, go ahead and use the commutative law to do some rearrangement, you're going to take your 3, park it next to your 2, take your 10 to the fourth, park it next to your 10 to the fifth. And now 2 times 3 gives you 6, and 10 to the 4 times 10 to the 5th, well, by the additive law of exponents, we just add these exponents together, we get 10 to the 9th. So we have 6 times 10 to the 9th. What we can do above is use this same trick. It's true that 38.547249,342 multiplied with 43,591, 278, 425 is just really nigh impossible for me to do it by hand. If we instead count the number of digits that exist past the 38, so in this instance, I have 1, 2, 3, 4, 5, 6, 7, 8, 9. What I'm going to do is this. I'll keep 38 because 38 is a number that's it's pretty easy for me to work with. But I'll multiply 38 by 10. That is going to be raised to the exact number of digits that are behind the number that I can actually work with. So I can work with the number 38. So I will count the numbers behind this digit. And in this instance, there are 9 digits behind the 38. So I can rewrite this 38, 5, 47, 249, blah, 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 as 38 times 10 to the 9th. And I can do the same thing here. While I can work with 43, because 43 is a manageable number, this 43, 591, 278, 425 is a little bit difficult for me to work with. So I'm going to do is I'm going to count the number of digits. I've got 1, 2, 3, 4, 5, 6, 7, 8, 9 digits here. So I'll take 43, I'll multiply it by 10, raised to the 9th. And now we can perform this calculation instead. We'll say that 38, 547, 249, 342 times 43, 591, 278, 425. That's going to be roughly equal to 38 times 10 to the 9th times 43 times 10 to the 9th. And at this point in time, you can kind of shuffle around your numbers. You'll have 38 times 43 times 10 to the 9th times 10 to the 9th. And so 10 to the 9th times 10 to the 9th, that's going to give me 10 to the 18th. That's so ridiculous. 38 times 43, but we can do that by hand. So we've got 43 times 38, 8 times 3, 8, 16, 24. We'll drop the 4, carry the 2. 8 times 4 is going to be 32, plus 2 gives you 34. Drop a 0, 3 and 3 is 9, 3 and 2 is 12. Add everything together, you got 4 and 0 is 4, 9 and 4 is 13, carry your 1. 1 and 3 is 4, 4 and 2 is 6. So you've got 16, 34 times 10 to the 18th. And that is a much better answer. That's going to be a much quicker way of doing business than dealing with all of these ridiculous numbers that are, at the end of the day, meaningless for all intents and purposes. And actually 163, well, I'm sorry, 1634 times 10 to the 18th is it is a very, very ridiculous number as well. So that's going to be like, if we're talking about miles, it's like half the distance across the solar system itself, or some ridiculous amount. So it's really, really, really ridiculously big. All right, let's do another example. So say you've got some big number like 15,342, 249, 740 times 23, 8, 24, 329. And we're multiplying these two really, really big numbers together. 15 is a pretty manageable number. I can definitely measure out 15 of something, even if it's 15 really big somethings. So I'm going to keep the number 15, or that's the general principle, is I can keep whatever quantity I can actually physically measure out. But what we'll do is we'll multiply this 15 by 10 raised to the number of digits that fall behind the value 15. So in this instance, we have 1, 2, 3, 4, 5, 6, 7, 8, 9 digits. So we'll replace this 15, 342, 249, 740, 740 rather, as 15 times 10 to the 9th. And we will do the same thing. 23 is something that I can actually physically measure out. So I'm going to say 23. But 824, 329, I probably don't need those numbers. So I'm going to say we'll do 23 times 10, and we'll count the number of digits behind the 23. And in this instance, we have 6 digits, so I'll multiply 15 times 10 to the ninth with 23 times 10 to the sixth. By the associative law, we can remove our parentheses. We'll just have 15 times 10 to the ninth times 23 times 10 to the sixth. We can move our 15 and 23 around. You'll have 10 to the ninth and 10 to the sixth. 15 times 23, we can easily move off to the side of our paper and do that calculation, but 10 to the ninth times 10 to the sixth, that's going to be 10 to the 9 plus 6, or 10 to the 15th. All right, so let's do 15 times 23. 3 times 5 is 15. Carry your 1. 3 and 1 is 3. Plus 1 gives you 4. Drop a 0. 2 and 5 is 10. 2 and 1 is 2. Plus 1 gives you 3. Add everything together. You get 3, 4, 5. So you've got 345 times 10 to the 9 plus 6, or 345 times 10 to the 15th, which is a massive number. There is one caveat. Usually, when we say that we can measure out something on a physical level, that's the same thing as what we call in science the level of significant figures. So while I said, yes, it's nice for me to make this calculation of 15 times 10 to the ninth times 23 times 10 to the sixth, and you can actually do this calculation. Usually we're going to determine not what is necessarily the most convenient for us, but rather the level of significant figures, the level of the degree of accuracy, said another way, of whatever measuring tool we have available to us in that moment in time. So if we don't have a measuring tool available to us, maybe measuring 100th of something is the best we can do, or measuring in the teens, in the tens of something is the best we can do. But usually you're going to basically rewrite these really, really big, or conversely, really, really small numbers based on whatever measuring tool that you have that's available to you. And the measuring tool will determine what is known as the degree of significant figures, or the level of significance of a calculation. So what does that mean to you? Well, when I rounded to 15 times 10 to the ninth, what I'm really saying is I have two significant figures here. And when I rounded to 23 times 10 to the sixth, I similarly said that, I can keep track of these two digits, the 2 and the 3, and that's it. And everything else, I'm okay if I round. So this is really the same thing as saying that I have two significant figures. Generally speaking, for hand calculations, when we're just doing a rough estimate, two significant figures of accuracy is all well and good. When you're doing something that is for an engineering purpose, a general engineering purpose, meaning it's not super, super precision purpose, but just a general calculation, what we usually tell students is 3 significant figures is ideal. So the most ideal way would be to at least measure out to the hundreds of something, or the hundredths of something, conversely. And that allows you to have what is known as three significant figures. Now, if we were to rewrite this big number with 3 significant figures, not that much changes. Get a more accurate answer, but you'll see that the answer isn't substantially different. So we were initially multiplying 15, 3, 4, 2, 2, 4, 9, 7, 4, 0 by 2, 3, 8, 2, 4, 3, 29. And what we say is, suppose I wanted to keep track of 3 significant digits. So I could keep track of the 153, and I could keep track of the 238. If that was the case, then we count the numbers behind these values, these digits, and you'll note that now I've got exactly 8 digits. So you'd say I've got 153 times 10 to the eighth, and I'm going to be multiplying this by, well, I could keep track of the 238 because I have three levels, three significant figures. So you keep track of the 238, but I'm going to be multiplying by 10 raised to the fifth because now I have only 5 digits behind my 238. By the assistive law, we can remove the parentheses. I'll have 153 times 10 to the eighth times 238 times 10 to the fifth. And we can do a little bit of arrangement. So I'll have 153 times 238 times 10 to the fifth times, times 10 to the eighth, rather. And this will be times 10 to the fifth. So we do 8 plus 5. That should give us 13. Because our exponents will add. We go to the side of our page. We'll do 153 times 238, which is a somewhat longer calculation. 8 times 3 gives me 24. Carry your 2. 8 and 5 is 40, plus 2 gives you 42. Carry your 4. 8 and 1 is 8, plus 4 gives you 12. Drop a 0. 3 and 3 is 9. 3 and 5 is 15. Carry your 1. 3 and 1 is 3, plus 1 gives you 4. Drop 2 zeros. 2 and 3 is 6. 2 and 5 is 10. 2 and 1 is 2, plus 1 gives you 3. Add everything together. You get 4, 11. 2 and 1 is 3. 3 and 5 is 8. 8 and 6 is 14. You get 1 and 1 is 2. 2 and 4 is 6. And a 3 is left over. So this is going to be 36414 times 10 to the 13th. And you might say, yeah, but Mr. B, we've got 345 times 10 to the, what do we say, 15 here. And now you've got 36414 times 10 to the 13th. And which is actually a better answer? Let's think about this for a second. Consider that there are 5 digits here, whereas there's only 3 digits for our other answer. If we were to think about changing this 36414 to something that only has 3 digits, you could say that this is roughly 364 times 10, and then you could say that these are zeros, so that would be 10 to the second power. So if you did that, you would say this is 364 times 10 to the second, and 10 to the second times 10 to the 13th. Well, the exponents adds, that's really 10 to the 15th. So now you got 364 times 10 to the 15. Is that really substantially different than your original answer of 345 times 10 to the 15th? And to answer that question, it really just depends on how important the 45 is compared to a 64. It depends on how much money is at stake. It depends on if lives are at stake in that calculation as to whether or not that was really worth you going through the extra hassle of dealing with 3 significant figures. But nevertheless, that's basically the idea, guys. We're going to essentially rewrite these really, really big numbers as numbers that are a little bit more manageable. We generally speaking want to keep 3 significant figures, but in your textbook, it's going to tell you how many significant figures you need to keep a hold of. So if it's 3, you're going to keep the first 3 digits. If it's 1, you keep the first digit. If it's 2, you keep 2 digits. Everything afterwards just becomes a bunch of zeros. So you count the number of digits behind the values that you keep, and you basically say that the values that you keep are going to be multiplied by 10 raised to however many digits are behind those values that you can't account for. All right. And this is true for really, really big numbers, but it's also interestingly true for really, really small numbers, because when you talk about really, really small numbers, what's interesting about raising things to the power of 10 is that it equally applies, the rules equally apply for really, really big numbers as for really, really small numbers. So when you talk about something like, we'll say 1/10 of an inch, well, it turns out 1/10 of an inch by our exponent rules is the same thing as 10 to the negative 1, because 10 to the negative 1, you'll remember from the negative exponent laws, is 1 over 10 to the 1. And 1 over 10 to the 1 is just 1 over 10. So if we're talking about tenths of an inch, that's really 10 raised to the negative 1 inches. Okay? If we're talking about, say, hundredths of an inch, that's the same thing as 10 to the negative 2 inches. If we're talking about thousandths of an inch, measuring something to a thousandth of an inch of accuracy, so really, really precision-bearing applications, that's the same thing as 10 raised to the negative 3. And if you're talking about things that are like really, really small, like the individual transistors inside of a microprocessor, something between, say, 10 to the negative 4 and 10 to the negative 6, you're going to have a 1 over 1 followed by some amount of zeros. Now, when we write this as a decimal, remember that 1/10 is the same thing as 0.1. 1/100th is the same thing as 0.01. 1/1000th is the same thing as 0.001. 1/10,000th is 0.0001, so on and so forth for smaller and smaller numbers. Okay. Now, when we write really, really small numbers, the issue of measuring things that are really, really small becomes very, very apparent. If you were to measure one, say, 10,000th of an inch, you would need, of course, a microscope for you to be able to actually, see something that's at the scale of 1/1000th of an inch. So if you wrote down, say, an engineering calculation or a calculation for a CNC machine, and it came up with this value, 0.01234 inches, because the machine itself is incapable of reading out these really, really small values, the 0.00, say the 0.34 value here, this really, really small 34. It's like what does it say? With 3/10,000ths of an inch, 4/100,000ths of an inch. But these are really, really ridiculously small measurements to make, and it's going to be most likely outside of the ability or outside of the capacity of a machine to actually calculate those really, really small values. It's not impossible. Okay, it depends. If you've got precision machining tools that are able to do that, then that's one thing. But usually speaking, it's going to be very, very difficult, very, very challenging for us to do it. So instead, we may rewrite this really, really small number as something else. And how we do that is you can basically count back a specific number of zeros from, say, the 1 and 2. And you could say that this is the same thing as 12 times 10 to the negative 3. So if you say this is 12 times 10 to the negative 3, where we get the negative 3 by essentially counting the number of digits that are behind the significant figures. So if we're saying that we want to keep track of things that are as small as the thousandth place, then we've got 3 digits that are behind the decimal point. And so we can rewrite this number as whatever the numbers happen to be times 10 raised to the negative third power. So since there's a 1 and a 2 or a 12, that is essentially from the third decimal, from the 1,000th place, there is a 0.012, or there's a 12/1000ths of an inch of something. You can rewrite this as 12 times 10 to the negative 3, and that would actually be a number that you can keep track of. So if you were to say, I don't know, multiply really, really small quantities together for some reason, say you were multiplying 0.01234 with something else that was really, really small, 0.054321, okay, inches. Because again, our machine, whatever we're using, if we're just using a machine for general purpose applications. We're not, say, in a precision engineering, precision machining environment. We don't have precision tools available to us. We're not using an electron microscope. We're not using a scanning electron microscope. We've just got the regular run-of-the-mill tools that aren't, $10,000 and above. Then what we can do to actually do this calculation without deceiving ourselves about the amount of accuracy is we can keep track of 3 digits, 3 decimal places behind the decimal itself. And in this instance, you've got a 5 and a 4. So you can rewrite this as 54 times 10 to the negative 3 because you've got exactly 3 digits that you want to keep track of. Okay. If you were to multiply these two quantities together, by the associative law, you can, of course, remove the parentheses. So you would have 12 times 10 to the negative 3 times 54 times 10 to the negative 3. And you, by the commutative law, rearrange your terms, your 12 and your 54 together. So you have 12 times 54 times 10 to the negative 3 times 10 to the negative 3. Well, 12 times 54, you can actually perform that calculation by hand. 2 times 4 is 8. 2 times 5 is 10. Drop a 0. 1 times 4 is 4. 1 times 5 is 5. Add everything together. 8 and 0 is 8. 4 and 0 is 4. 1 and 5 is 6. So you get 648. And what happens to your tens is that you've got 10 to the negative 3 times 10 to the negative 3. So you'll have 10 to the negative 3 plus negative 3. Or said another way, 10 to the negative 6 power. And that's pretty good. That's a pretty good answer. Of course, it depends that the number of digits that you want to keep depends on the specific application that you have available to you. So, what we just did was we kept 3 significant figures. If you keep track of 3 digits behind your decimal place, so the 0.012 and the 0.054, that's 3 significant figures. Okay. That's good enough for most applications because many calipers in the United States, caliper being the tool that you use to actually measure out things that are that small, will measure to 1,000th of an inch accurately. And so if you need to measure out 54 thousandths of an inch, you can do that. You can actually physically do that without having some sort of a special $1,000 or $10,000 or $100,000 piece of machinery in order to measure out something that is even smaller. So you can measure out 54 thousandths of an inch and you can measure out 12 thousandths of an inch. So what we like to say to students is, yes, keep track of 3 significant figures. However, if you did not have a caliper tool set available to you, if you're just measuring in, say, tenths of an inch, and say you have a number like 3.1425 times, we'll say this is 4.27819, okay? And say we're making this calculation, 3.1425 times 4.27819. And we actually don't even have an ability to measure out to anything smaller than, say, a tenth of an inch. Okay, we have one significant figure of accuracy. So what we would say is that because you have only one significant figure, you could rewrite this first number as 31. And how many digits are we keeping track of? Well, we're keeping track of the 1 here that's behind our decimal place. So we would say that this is the same thing as 31 times 10 to the negative 1, since we're keeping track of that first decimal. And similarly, if I'm keeping track of the little 2 here, because I can only say measure out to a tenth of an inch, then I'd say I've got a 42 times 10 to the negative 1. And if we do this calculation, we could do 31 times 42 times 10 to the negative 1 times 10 to the negative 1. Of course, we can do by hand 31 times 42. 1 times 2 is 2. 1 times 4 is 4. Drop a 0. 3 times 2 is 6. 3 times 4 is 12. Add everything together. 2 and 0 is 2. 4 and 6 is 10. 2 and 1 is 13. Sorry, 2 and 1 is 3. And 1 gives you 13. So you got 1302 times 10 to the negative 1 times 10 to the negative 1 will be 10 to the negative 1 plus negative 1. Of course, that gives you 10 to the negative 2 as an answer. Excellent. Excellent, excellent, excellent. Okay. Interesting things happen in mathematics whenever you're doing these scientific notation style calculations, especially in an engineering context, where you may be utilizing what is called the SI system for a lot of your calculations. Um, when you do these SI calculations, you may have like 4.7, sorry, 4 times 10 to the 7th. So say you did all of these different calculations and you plugged it into one of these formulas that you were using for either a machining application or an engineering or a banking application. And all of a sudden you've got 4 times 10 to the 7th times 5 times 10 to the 6th, and that's all being divided by 3 times 10 to the 7th. Well, one more reason for why SI notation is really, really nice to use, especially when we can't accurately account for really, really big quantities to begin with, is the fact that when you do rewrite your numbers in terms of SI notation, many of these division operations are going to become really, really quick for you to actually perform. So let's go through this together, shall we? All right, so 4 times 10 to the 7th times 5 times 10 to the 6th. By the commutative law, we can go ahead and move our numbers together and our exponents with exponents. So we'll move our 4 and our 5 together. We'll get our 10 to the 7th, and we'll multiply it by 10 to the 6th. And then you'll have 3 times 10 to the 7th in the denominator. All right, so 4 times 5, of course, that's 20. And so you'll have 20 over 3 in your denominator. But look what happens. 10 to the 7th, that's going to cancel out with 10 to the 7th in your denominator. And so now, look at this. This is pretty magical. You've only got 10 to the 6th left. So you've got essentially 20 over 3 times 10 to the 6th. Now you can calculate that out. You can go to the side of your page, do some long division, 3 into 20. Okay, 3 into 20 goes, let's say 6 times. 6 times 3 gives you 18. And then you get 2. So if you wanted a more accurate answer, you just keep doing this again. And it looks like you'd get 6.6666. So 6.666 times 10 to the 6th. And that's pretty much all you can do if you really wanted a decimal style answer. That's not too bad, not too bad. And I hope that I've convinced some students that this SI notation has a little bit of validity. Now, and many times, if you're a nursing student and you have to take those chemistry classes, you're going to be dealing with really, really small numbers divided by really, really small numbers. And so the same rules apply. You could have something like 2.8 times 10 to the negative 15 all over 3.2 times 10 to the negative 12. And it's like, what do you do with this nasty nonsense? Well, naturally, we could, in fact, try to do some division with this 2.8 and 3.2. We could do division of decimals, shall we say? But what we learned in class in Math 900 is that instead of doing decimal division with other decimals, if you count the number of decimal places, in this instance, we have 1 digit behind the decimal, right? And 1 digit behind the decimal. You could rewrite this as 28 times 10, and we can rewrite this 30.2 as 32 times 10 times 10 to the negative 12. Now, the reason you would want to do that is that in this instance, your 10s are going to cancel out anyways. So it turns out that 2.8 divided by 3.2 is the same thing as taking 28 and dividing it by 32. Obviously, it's a lot easier for us to work with 28 and 32 than it is for us to work with 2.8 and 3.2. 28, of course, we know is going to be 2 and 14. 14 is the same thing as 2 and 7. And if we do prime factorization on 32, you should see that 32 is the same thing as 2 and 16. 16 is the same thing as 2 and 8. So what we can do here, so we can rewrite this using prime factorization, we say this is 2 times 2 times 7 on top, and it is 2 times 2 times 8 on bottom. 2's naturally canceling out. Very convenient. And then what happens to the 10 to the negative 15 divided by 10 to the negative 12 is that there are two ways to think of this. On the one hand, you can use exponent subtraction, which is probably the easiest way to think of it. But on the other hand, you can use one of your negative inverse laws to flip your 10 to the negative 12 to the other side into exponent addition. But regardless of how you do that, what's going to happen is you'll have 7/8 and 10 to the negative 15 minus the negative 12. Well, that's going to be 10 to the negative 15 plus 12, which of course, if I owe you $15, but I pay you back $12, that's going to give me $3 left over. So this is 7/8 times 10 to the negative 3. Now, students might be saying, oh my goodness, there's so many steps, but look, once you get the hang of being able to, or what, not necessarily the hang of it, but rather once you build it up enough confidence where you understand, yes, it's okay for me to move this decimal place one space and multiply by 10, which is what we learned in Math 900, then everything else in terms of this calculation just follows naturally without ever having to pick up a calculator in order to perform the calculations. Once you get to 7/8, you can look up in a machinist chart if you had to, or in many instances on the factory floor, 7/8 of an inch, they'll have usually an inch to decimal conversion for some of these, fractions that appear a lot in machinist calculations. So even if you had to measure using a decimal place, well, yes, it's true. We could do long division of 8 into 7 in order to find, say, the decimal equivalent. 7/8 will generally be one of those fractions that in a factory floor environment, people just, remember, or they just memorize that this is going to be roughly equal to 0.875. So 0.875 times 10 to the negative 3 would be your best answer if you actually were measuring using the decimal system. Okay, that's pretty much all there is to chapter 5.6. There's really nothing more to know about the SI notation system. It's used a lot in your chemistry and your physics classes. So when you get to those classes, you'll be reintroduced to this idea. And as you go through your higher level math courses from college algebra, they'll reintroduce this idea to you. In your calculus classes, they're going to really, really introduce this idea to you. So this idea will keep coming up over and over and over again. And so you're going to have a lot of opportunities to really master the SI notation as you go through the ranks, because it's a fairly important way to be able to perform or shortcut through calculations. All right, so without further ado, let's dive into chapter 6.1. Factoring. The basic idea of factoring is that factoring is distribution in reverse. There are many, many instances where you're going to encounter situations where you have to do division, where the division operation itself is not as straightforward as just, being able to perform the long division that we're ordinarily used to. In instances where you're dealing with, say, I don't know, Two polynomials. Say 3 times x squared plus x divided by 4 times x squared plus x. The question that would be asked to students is, what is this equal to? I think I have another sneeze coming out. I'm sorry, guys. I'm way under the weather. It's terrible. It's the time of the season. Okay. So a wrong answer that students will usually give on an exam or a standardized test is they'll actually start canceling out terms. So they'll say, okay, this must be 3/4. So this would be a wrong answer because they'll divide their x squared with x squared and x with x. And that would be okay to do if it was 3x squared times x over 4x squared times x. In this situation, because you can break open your fraction and you can essentially write 3x squared times x as 3/4 x squared over x over x. These terms will in fact divide out. Your x squared divided by x, that just becomes 1. Your x divided by x just becomes 1. And you have 3/4 left over. So you have 3/4 times 1, or simply 3/4. But that's not what you've got here. You've got 3x squared plus x all over 4x squared plus x. And so kind of what you're doing is similar to the mistake of, say you've got 3 plus 9 divided by, we'll say this is 3 plus 3. Okay? So say you've got 3 plus 9 divided by 3 plus 3. And a student said, all right, well, I can divide these 3's out. And 3 goes into 9 3 times. So my answer is 3. But really what's happening by the associative law is 3 plus 9 is actually something inside of a parentheses. And 3 plus 3 is also, or the terms in your denominator, are similarly, by the associative law, something that should be inside of a sequence of parentheses. And so really what you've got is you've got 3 plus 9, or 12, divided by 3 plus 3, or 6. 12 divided by 6 gives you 2. So you don't just divide out terms that are on top of one another if those terms are separated by an addition symbol. Because what happens when you've got an addition symbol is you really can only break up your fraction into two fractions that have the same denominator. That's about as good as you can do, is just start breaking up your fraction into a sequence of terms that have the same denominator. That's about as good as you can get. Okay. And of course, you would never do that because that's actually going backwards. So it wouldn't even make sense to do that in a student's mind. But that's like what you can actually do according to the rules of algebra. You can't just cancel out terms on top of each other. We have to watch out for that. Okay. So what can we do? Well, in order for us to actually perform this division operation where we've got 3x squared plus x divided by 4x squared plus x, is we're going to need to use factoring. And how this works is factoring is actually the same thing as distribution in reverse. According to the distribution law, you guys will recall that anytime you have a number that's parked out in front of a sequence of terms, you can take that number and multiply across the terms that are being added or subtracted from one another. So if you had 3 terms, you do that 3 times. If you have 4 terms, you do that 4 times, so on and so forth. And so here's the deal. If you were to take this 3x squared plus x and you expand it, what you're going to see is the x squared is going to equal x times x, right? The reason you would want to expand x squared to x times x is that now it becomes plain to see that you have a term that exists in common between 3x squared and x. This is known as your GCF of a polynomial expression. So the long and the short of it is, when you've got a polynomial expression such as 3x squared plus x divided by another polynomial expression such as 4x squared plus x, one of the ways that you can go about attempting, and I should say that double with emphasis, attempting to actually divide out those terms is, because in many instances you won't actually be able to do this, but is to expand out the expression and look for what is known as the GCF of a polynomial. Because once you find that GCF of the polynomial, you can rewrite the polynomial using the rules of distribution. I can take this x out, put it out in front, and whatever we have left over, I can write it as a sequence of terms that is inside of my set of parentheses. So I pull my x out, and you'll see that I have a 3x left over. So I can write as 3x inside of my sequence of parentheses. But here's the deal. Your x doesn't just disappear, right? This x is actually, or can actually be thought of as 1 times x. And so when you quote unquote take out the x value from this second term, you have to remember that there, in fact, is a 1 that will be multiplied by the x, or this placeholder 1, which will allow your calculation to remain balanced. Okay, so your terms aren't just disappearing into the ether. And so when we do that, we can now rewrite this top expression as x times the quantity 3x plus 1. But we can also do the same thing for the bottom expression. For the bottom expression, you've got 4x squared plus x. And if we expand out the x squared, you'll see that we can rewrite this as 4 times x plus x. And there is an x in common. So we can do the same thing here. We'll take out our x, and we'll write x times the quantity 4x plus 1. And so only now can you actually divide out your terms, because I hope everybody can see you've got an x term and an x term. So those will divide out, and your answer would be 3x plus 1 over 4x plus 1. So 3x squared plus x, you would find, or rather 3x squared plus x over 4x squared plus x would be equal to 3x plus 1 over 4x plus 1, using the technique known as factoring. Okay, so that's the application case. What we're going to do in this chapter, we will get back to these applications using what are known as rational expressions. This is an application using rational expressions. We'll come back to this, but what we're going to do is we're going to hunker down on all of the different ways that we can actually begin to rewrite these polynomial expressions so that at some point in time, when we're dealing with these more complicated engineering and or calculus problems where you have polynomials divided by polynomials, you can actually simplify those problems and get an answer that looks nice. Obtain a nice looking answer so that you don't necessarily have to resort to a computer in order to perform your calculations. Now, of course, this idea is a little bit antiquated now that we have computers, right? We didn't always have computers available. And in some places around the world, you still don't necessarily have computers available. But in most places, even if you're in, say, Nigeria, okay, or in many of these places that are often thought of in the West as being really, really poor, they do, in fact, have computers, guys. They do, in fact, have cell phones. You'll see if you go to India, you can go to the slums of Mumbai, and everybody has a cell phone in the slums. Okay. These people may be poor, they may be impoverished by like American standards, but I guarantee you they still have access to cell phones. And so we need to keep that in mind. Um, so these techniques, they were essentially developed in a time where you didn't have computers in order so that you could perform calculations without computers. Now that we have computers, a lot of these calculations would probably be best to just break out the computer and let the computer do it, unless you're looking for creating like the most efficient, say, calculation that you could possibly make, and in which case some of these techniques will still be applicable. So nevertheless, we are still going to teach these techniques regardless of the fact. So first of all, most of our techniques are going to rely on being able to find a GCF at some point in time. Doesn't matter how complicated the technique gets, at the base level, the base idea is we're just using the GCF. So the GCF is going to be a factoring technique that you could say all of the other factoring techniques are built off of. So it behooves us to understand how it works. So say you want to find the GCF of three numbers, say 24, 40, and 72. First of all, the question is, what is a GCF? GCF stands for greatest common factor, which we learned in Math 900. And what that means is it means that when you calculate the GCF, you're essentially finding the biggest number that you can divide all three terms by. In a math sense, what is the GCF? The GCF is this value which will allow you to essentially perform distribution in reverse. Okay, when you have a sequence of terms that are added or subtracted from one another. But for now, when we're just calculating, say, the GCF of two or more numbers, we're just finding the biggest value they can divide into each of these numbers. All right, so how does that work? Well, you'll remember the method of prime factorization. In Math 900, I taught you that you essentially divide out whatever numbers you're given. Maybe you're given the number 24. So you'll recall that 24 is the same thing as 2 times 12. And 12 is the same thing as 2 times 6. And 6 is the same thing as 2 times 3. So you'd be able to rewrite 24 as 2 times 2 times 2 times 3 if you look at the base prime factors that you're working with. You can similarly do the same thing with the number 40. 40 is the same thing as 2 and 20. 20 is the same thing as 2 and 10. 10 is the same thing as 2 and 5. Number 72. 72 is the same thing as, what do we say? 9 and 8 gives us 72. 9 is the same thing as 3 and 3. 8 is the same thing as 4 and 2. 4 is the same thing as 2 and 2. Okay, so you'd say that 40 is 2 times 2 times 2 times 5, because those are the lowest term in your factor tree diagram. You'd say that 72 is the same thing as 3 and 3 and 2 and 2 and 2. So 2 times 2 times 2 times 3 times 3. All right. So what do we do with this information? Well, what I teach in Math 900 is I teach an algorithmic technique where I tell you line up all of your prime factors, almost like a table. So you found that these are the prime factors for each of these numbers. We're going to give ourselves a table. What you do with this table is you're going to cross out factors that are in common with each of the terms, and you write that factor once in your table. So you see how you have a set of 2's that are all in common? I'm going to cross out all of my 2's, and I write it exactly once inside of my GCF table. I have another set of 2's. I'm going to cross those out. I'll write it exactly once in my GCF table. Got another set of 2's. Cross them out. I'll write it exactly once. So the GCF of 24, 40, and 72 happens to be 2 times 2 times 2. 2 times 2 is 4. 4 times 2 is 8. So the GCF is 8. And indeed, 8 will divide 42. I'm sorry, 8 will divide 40. 8 will divide 24. And 8 will divide the number 72. In a more abstract case, when we're talking about factoring polynomial expressions, what we're going to actually look for is we may need to find the GCF of 2 or more polynomial expressions. You may need to calculate, say, the GCF of 8y squared and something like 12y squared. And the question is, what would this be equal to? Because, for a student, it makes sense that you'd perform prime factorization on numbers that don't have any variables. But then once you start tossing in variables, the student will often think to themselves, I don't know what to do because I don't know what y is, so I don't know what y squared is. And while that's true, what we need to know is simply that a variable is just a number on the one hand, and we assume that the number, or we treat these variables as if they are prime factors. Okay, so whatever y happens to be, we're going to just treat the y as if it is a prime factor of the expression itself. Like we don't know really what y is, but the best we can do is just treat it as though it's a prime factor, because any instance where you would have a y divided by y, you would essentially divide out your y's anyway. So it's going to act like a prime factor in an expression, even if y itself wasn't, say, prime per se, but it's still going to behave that way. So when we're calculating these GCFs, you're going to take your number, such as 8y squared, and first of all, expand it out. So you'd say this is 8 times y times y. And then what you're going to do with the actual numeric component is you're going to find the prime factors of that numeric coefficient. So in this instance, a coefficient in front of our y squared is 8. So we'll create a factor tree diagram for the number 8, and you'll see that 8 is the same thing as 2 times 2 times 2. So when we expand out 8y squared, we actually get 2 times 2 times 2 times y times y. We're going to do the same thing for whatever other terms we might be given. If I want to know what the GCF of, say, 8y squared and 12y squared happens to be, I'm going to need to not only factor the 8y squared, but I'll also have to find the factor tree diagram, the prime factors of, say, 12. So what we'll find is that 12 is the same thing as 2 times 2 times 3, and y squared is y times y. So what we do with this information is giving ourselves a little bit of a table where we write GCF. We're going to write 8y squared, and you found that was 2 times 2 times 2 times y, and we found 12y squared was equal to 2 times 2 times 3 times y. Here's what we do. We are going to cancel out our sequence of 2's. We'll write the 2 once. Here's my sequence of 2's. I'll write the 2 once. You'll see I have a y in common. I write that once. I have another y in common. I'm going to write that once. 2 times 2 is 4. Y times y is y squared. That is my GCF. Okay. It doesn't matter how complicated the expression gets. We could have something that's super nasty looking, like this. We can still find a GCF. So suppose we wanted to find the GCF of 10x to the 5th, y to the 4th, 15x squared, y to the 3rd, 25x to the 3rd, y to the 5th. The question is, what are we going to do? Well, first of all, give yourself some space. One of the things that a lot of students don't do correctly is they don't give themselves sufficient room to work with. What I'm going to do is I'm first going to try to factor whatever the coefficient, whatever the number happens to be in front of the polynomial expression. So in this instance, you've got 10x to the 5th, y to the 4th. 10 is the same thing as 2 times 5. So you'll factor 10, giving yourself the prime factors, 2 times 5. X to the 5th is just x times x times x times x times x. Y to the 4th will be y times y times y times y. So that's all I can do. That's all I can do with 10x to the 5th, y to the 4th. I can just rewrite it like that. Okay, but I'm going to do the same thing for all of these. So I've got 15x squared y to the 3rd. 15 is going to be the same thing as 3 and 5. X squared is x times x. Y to the 3rd is y times y times y. That's just from the definition of exponents. For our last term, we've got 25x cubed y to the 5th. 25 is the same thing as 5 times 5. X cubed is the same thing as x times x times x. Y to the 5th is the same thing as y times y times y times y. So, giving yourself a little bit of a table, when you go to calculate the GCF, you're just looking for terms that exist in common. So I've got a sequence of 5's. all of those terms are in common, I'm going to write a 5 in my table once. I have a sequence of x's. I'm going to write another x in my table. I have a sequence of x's. Write an x. I think that's about it for my x's. I've got a sequence of y's. Write a y down. Another sequence of y's. Another sequence of y's. And that's about as good as it gets. So my GCF for this expression is 5x squared y to the third. One word of caution, the GCF doesn't just extend to these polynomial expressions, but it also extends to any number of more complicated sequences of terms that you may encounter. If you had, say, 3 times x minus 1, and say you were trying to calculate, I don't know, the GCF of 3x squared, I'm sorry, 3 times x minus 1 and 8 times x minus 1. The thing of it is that x minus 1, being that it is its own independent term, meaning if you knew what x was, you would know what x minus 1 would happen to be. In this instance, x minus 1 is treated as though it's its own number that's independent. And since these numbers are in common, if you were to calculate the GCF of, say, 3 times x minus 1 and 8 times x minus 1, well, the only things that are in common are going to be the x minus 1 term. So if you have the GCF of really, really complicated terms, like 4 times x squared plus z squared, say it's something like this, really nasty. Here again, the x squared plus z squared would be treated as though they were their own, it was its own separate like number that's being multiplied with the 4. And the x squared plus z squared that's multiplied with the 6, it would be treated like its own number that is being multiplied with the 4. The only thing you would have to do here in this instance is just remember that you need to factor your 4 term. So 4 is the same thing as 2 and 2, and 6 is the same thing as 2 and 3. So really this 4 times x squared plus z squared, that's the same thing as 2 times 2 times x squared plus z squared. And this 6 times x squared plus z squared, that's the same thing as 2 times 3 x squared plus z squared. So when you go to calculate your GCF, now what we're doing is, yes, while it's true, I've got to consider this x squared plus z squared term as though it's its own number, but that's not the only thing that's in common. I also have to consider the 2's that are in common between the 4 and the 6. So just watch out. As you're going through the chapter, you will see problems that are going to be more complicated, such as the one here. So you can have more trickier looking GCFs. Just remember, anything in parentheses is treated as though it's its own separate quantity or its own separate number. All right, so what does this have to do with factoring? Apart from, say, reducing what is called a rational expression, where you have one polynomial divided by another polynomial. Well, in general, when we approach a polynomial expression, such as, let's say we've got something like 16y cubed minus 12y squared plus 4y. Here, this is called a polynomial expression. On the one hand, this polynomial expression is special because it's what is known as a trinomial. It has 3 terms, and trinomials are really, really special polynomials, as it turns out, because you can do a lot of things with trinomials by hand without the assistance of a computer. And so what we can do with this particular expression is, while it's okay for us to perform calculations with this expression such as it is, it may also be the case that we, for one reason or another, may need to rewrite this expression by using what is called factoring. And when we factor this expression in this particular instance, we can utilize what is known as the GCF method. So factoring using the GCF, that is what we're learning. Factoring using the GCF. The GCF. So we're going to take a polynomial expression, such as the one you see before you. We are going to, first and foremost, find the factors of each of the terms, each of the numeric terms that are in front of these variables, if you will. Because that's something that you can do right off the bat. Like you can factor 16, you can factor 12, you can factor 4. We don't need to have we just need to remember our division laws. So 16 is the same thing as 4 and 4. 4 is the same thing as 2 and 2. 12 is the same thing as 3 and 4. This is 2 and 2. All right. So 16y cubed, if we were to just look at it by itself, that's going to be the same thing as 2 times 2 times 2 times 2. And then y cubed would be y times y times y. For the negative 12y squared, that's going to be a negative 2 times 2 times 3 times y times y. Watch out for the sign that's in front of your term. It is important. In some instances, we may need to do something with that. In this particular case, I don't think it will be necessary, but in many instances, you're going to need to keep a hold of that negative symbol just in case you want to factor out the negative, which is another technique which we'll learn here shortly. For 4y, you found this is 2 times 2 times y. All right, so if we're calculating our GCF, to calculate the GCF, we just essentially cancel out any terms that are in common. We found that there's a 2 in common. There's probably a y. There is a y in common. And I think that's about as good as it gets. No, I think we can actually factor out another 2. So we found that 4y is the GCF of this expression. So here's what we're going to do with that information. What we've just found is that we may rewrite this polynomial as 4y, and then in a sequence of parentheses, we are going to write what remains of the expression. You'll see that you've got a 2, and I'm actually going to increase the... Got 2 times 2 and y times y. Right here, you've got a negative sign, a 3, and a y. Okay, and here, for this term, you're just going to have a 1. Remember, when we do factoring, it's not like we're, you know, using a ray gun and just obliterating the numbers into nothingness or something. It's that we're actually dividing out this quantity from each of the subquantities that may be added or subtracted from each other. We're writing that out in front. So we've got 4y written out in front, and then the terms inside of the parentheses are what is left over from this division, quote unquote, process that we're doing. And we find that, as it turns out, 16y cubed minus 12y squared plus 4y can be rewritten as an expression 4y, and inside of a sequence of parentheses, you'll have 4y squared minus 3y plus 1. That's great. This would be your answer for factoring the expression. One last example. You're going to be given a problem, factor the expression. You'll be given something like negative 7a cubed and 14a. And the question is, what can you do with this? Well, to factor the expression, I'm not going to pull it to the side. All we're going to do is we're going to try to essentially expand out each of the terms. And 7 is prime, so there's nothing I can do with that. I can just write negative 7 times a times a times a. But for 14a, I can indeed break open 14 into being 2 and 7. So I'll rewrite 14a as 2 times 7 times a. Now, if I'm looking for a GCF, here's the thing. Have an A and an a 7 and a 7. I'm sorry, I don't have an A and an A. I don't know what I'm doing. Too trigger happy by A's. I've got a 7 and an A that is in common. Right? So my GCF on a technical level is 7A. And what's going to be left over is this negative A times A, or a negative A squared, and a positive 2. But in terms of like aesthetics, when you see this polynomial expression and you see how there is a negative sign here, generally speaking, we really want to avoid that, okay? From a perspective of tradition, if we're writing textbooks, if we're writing down expressions in a traditional manner, and you have like some negative term out in front, that's generally avoided because there are just a number of reasons why we try to avoid that. But how we avoid it is we are going to, my apologies, it's tapped aside here. What we're going to do is, well, it's true that we could indeed factor using in this particular manner. What we could do instead is keep track of the fact that whenever you have a negative, say you've got a negative, just a negative number, so negative b. Recall the negative identity law. It just says that negative b is the same thing as negative 1 times b. Okay. One of the interesting facts of negative numbers is not just that any negative in front of a number is the same thing as negative 1 times a number, but also the fact that when you have a positive number, check it out, guys, a positive number is the same thing as a positive number times a sequence of negatives. 7 would be, say, the same thing as 7 times a negative 1 times a negative 1. So negative numbers, said another way, are actually hiding inside of whole numbers, positive whole numbers. It's just that you don't see it. It's not that they're not there. It's just that you don't see it. And the reason is negative and a negative is a positive. So this would be the same thing as 7 times a positive 1. And 7 times 1 would give you 7. So it's perfectly legitimate for me to rewrite a negative as being a negative 1 times a number, but it's equally legitimate for me to write a positive number as being that positive number multiplied by a sequence of negatives. And why that's important is, while it's true I could have written negative 7a as negative 7 times a times a times a, or this negative 7a cubed rather, it's a negative 7 times a times a times a, I could have easily written it as negative 1 times 7 times a times a times a. And if I do that, then the way that I can kind of quote unquote clean up this expression is I can rewrite this second term as negative times a negative, 2 times 7 times a. Now, if I do that, it becomes clear to students that the 7 will cancel out, or rather that you have a negative 1 in common and a negative and a 7 in common, but then you also have an a in common. And so here what we're saying is negative 1 and 7 will be a negative 7. And so you'll have a negative 7a. So the negative 7a cubed plus 14a, because this is our new GCF, you can rewrite this as negative 7a. And what's in parentheses? Well, just like before, you're going to have an a times a. That'll be a positive a squared. However, for your bottom term, you've got a negative 1 times 2. So that gives you a negative 2. Now, I personally don't care if you were to rewrite this 7a cubed or negative 7a cubed plus 14a as 7a times the quantity negative a squared plus 2, or if you rewrite it as negative 7a times the quantity a squared minus 1. But from time to time, from time to time, you'll often see that this little trick, this little technique, especially as you go into pre-calc, especially as you go into this calculus courses, is going to be used over and over and over again to try to trick students up because many students are going to forget about this very, very simple fact of negative numbers. With that, guys, I've been droning on long enough. I will let you go. Take care. See you in class.